Welcome to the last lecture of the Plutus Pioneer program. Even though this is the last regular lecture, I intend to create a special lecture once it will be possible to deploy Plutus contracts to the testnet. And in this lecture, I don't want to introduce any new topics or concepts, but instead demonstrate another walkthrough end-to-end through a demo I wrote some months ago that clones the very popular Uniswap contract from Ethereum. So I'll demonstrate that and explain that. And the one new thing I want to show following the request that some of you had during the last Q&A session is I want to show how you can query the endpoints created by the PAB with curl commands just from the console. So for those of you who haven't heard of Uniswap, what is Uniswap? Uniswap is a so-called DeFi for decentralized finance application that allows swapping of tokens. In the case of Ethereum, it's ERC20 tokens on Ethereum without any central authority. So you don't need a centralized exchange, the traditional way to exchange tokens or other crypto assets, but everything is governed by smart contracts and works fully automatically on the blockchain. And another interesting feature of Uniswap is that it doesn't discover prices the usual way with a so-called order book, but uses a different automatic price discovery system. And the idea is that people can create so-called liquidity pools. So if they want other users to be able to swap two different tokens, then somebody can create a liquidity pool and put a certain amount of those two tokens in this liquidity pool. And in return, the creator of that pool will receive so-called liquidity tokens that are specific to this one pool. And then other users can use that pool to swap. So they take some amount of one of the tokens out in exchange for putting an amount of the other token back in. Additionally, people can also add liquidity to the pool and receive liquidity tokens as well. Or they can also burn liquidity tokens in exchange for tokens from the pool. And all these features are also implemented in the version of Uniswap that works on Cardano that I'm going to demonstrate now. So let's look at the various operations that are available in turn. It all starts by somebody setting up the whole system. So some organization or entity that wants to offer this Uniswap service. So it starts with a transaction that creates a UTXO at a script address that is here called factory for Uniswap factory. And it contains an NFT that identifies the factory, same trick that we have used a couple of times before. And as datum, it will contain the list of all liquidity pools. So in the beginning, when the factory is just being created, that list will be empty. Now let's assume that one user, Alice, wants to create a liquidity pool for tokens A and B, a pool that allows others to swap A against B or B against A. So she has to provide some initial liquidity for the pool. So she needs some amount of token A and some amount of token B. Let's say she has 1,000 A and 2,000 B. And it's important to note here that the ratio between A and B reflects Alice's belief in the relative value of the tokens. So if she wants to set up a pool with 1,000 A and 2,000 B, then she believes that 1 A is as value as much as 2 Bs. In order to create the liquidity pool, she will create a transaction with 2 inputs and 3 outputs. The 2 inputs will be the liquidity she wants to provide, so the 1,000 A and the 2,000 B, and the Uniswap factory, invoked with the create redeemer. And the 3 outputs will be the newly created pool. We call it pool AB here to indicate that it contains tokens A and B, which will contain the liquidity that Alice provided, the 1,000 A and the 2,000 B, and a freshly minted token that identifies this pool, an NFT. I call it AB NFT here. And the datum of the pool, the 1415, will be the amount of liquidity tokens that Alice receives in return for setting up this pool and providing the liquidity. And if you wonder about the number, that is the square root of the product of 1000 and 2000. So that's how the initial amount of liquidity tokens is calculated. It doesn't really matter. You could scale it arbitrarily, but that's the way Uniswap does it. The second output is the Uniswap factory again, with the same NFT as before that identifies it. And now the datum has been updated. So in this list that was empty before, the list of all liquidity pools, there's now an entry for the newly created AB pool. Finally, there's a third output for Alice, where she receives the freshly minted liquidity tokens that I call AB here to indicate that they belong to the pool AB. Now that the liquidity pool has been set up, other users can use it to swap. So let's assume that Bob wants to swap 100A against B. So what will Bob do? He will create a transaction that has two inputs and two outputs. The two inputs are the 100A he wants to swap and the pool with the swap redeemer. And the outputs are the Bs he gets in return. In this example, that would be 181 Bs, and the pool updated. So the pool now has the 100A that Bob provided additionally. So now it's 1100A, and it has 181B fewer than before. It still, of course, has the NFT that identifies the pool. And the datum hasn't changed because the amount of liquidity tokens that have been minted hasn't changed. So now, of course, the question is, where does this 181 come from? And this is this ingenious idea how price discovery works in Uniswap. So the rule is roughly that the product of the amounts of the two tokens must never decrease. So initially we have 1000 A's and 2000 B's, and the product is 1 times 2 million, so 2 million. And if you do the calculation, then you will see that after the swap, 1100 times 1819 will be larger than 2 million. And if you think about it, and maybe try a couple of examples by yourself, then you will see that in principle, you will always pay this ratio of the A's and B's in the pool, at least if you swap small amounts. So originally the ratio from A to B was 1 to 2, 1000 to 2000, and 100A is relatively small in comparison to the 1000 liquidity. So Bob should roughly get 200 B's, but he does get less. So there are two reasons for that. One is that the amount of tokens in the liquidity pool is never allowed to go to zero. And the more of one sort you take out, the more expensive it gets, the less you get in return. So 100 depletes the pool a bit of A's. So he doesn't get the full factor 2 out, he gets a little bit less out. That's exactly how this product formula works, if you think about it. And this also makes it so ingenious because it automatically accounts for supply and demand. So if the next person now would also want to swap 100A, he would get even less out. So the idea is, if a lot of people want to put A in and want to get B in return, that means the demand for B is high. And that means the price of B in relation to A should raise. And that is exactly what's happening. So the more people do a swap in this direction, put A in and get B out, the less they will get because the price of B rises. If there were swaps in the other direction, you would have the opposite effect. So if there's an equal amount of swaps from A to B and B to A, then this ratio between the two amounts would roughly stay the same. And there's an additional reason why Bob doesn't get the full 200 that he might expect, and that is fees. So we want to incentivize Alice to set up the pool in the first place. She won't just do that for fun. She wants to profit from that. So she wants to earn on swaps that people make. So this original product formula is modified a bit to insist that the product doesn't only not decrease, but that it increases by a certain amount, a certain percentage, depending on how much people swap. So that's, I think, 0.3% in this example of the 100A that Bob swaps. And it would be the same if you swap B instead. So this is basically added on top of this product. So anytime somebody swaps, the product actually increases. Not only does it not decrease, it actually increases. And the more people swap, the more it increases. And the idea is that if Alice now would close the pool by burning her liquidity tokens, she gets all the remaining tokens in the pool, and that would be more, the product would be higher than what she originally put in. And that's her incentive to set up the pool in the first place. The next operation we look at is the add operation, where somebody supplies the pool with additional liquidity. So let's say that Charlie also believes that the ratio from A to B should be 1 to 2, and he wants to contribute 400A and 800B. He could also have tokens in a different ratio. Basically, the ratio reflects his belief in the true relative value of the tokens. So Charlie wants to add 400As and 800Bs, and he creates a transaction with 2 inputs and 2 outputs. The inputs are the pool and his contribution, his additional liquidity. And the outputs are the updated pool, where now his A's and B's have been added to the pool tokens. And note that now the datum has changed. So we had 1,415 liquidity tokens before, and now we have 1,982. And the difference, the 567, go to Charlie. So that's the second output of this transaction, and that's the reward to Charlie for providing this liquidity, this additional liquidity. And there the formula is a bit complicated, but in principle it also works with the product. So you check how much the product was before and after the tokens have been added, and you take into account how many have already been minted. And that also ensures that now basically Alice profits from the fees that Bob paid with the swap and Charlie doesn't. So this is taken into account. But the specific formula doesn't matter. The idea is just that it's fair. So people should receive liquidity tokens proportional to their contribution. But if they only add liquidity after a couple of swaps have already happened, then they shouldn't profit from the fees that have accumulated in the meantime. The next operation we look at is called remove, and it allows owners of liquidity tokens for a pool to burn some of them. So in this example, let's assume that Alice wants to burn all her liquidity tokens. She could also keep some. She doesn't have to burn all. But in this example, she wants to burn all her 1,415 liquidity tokens. So for that, she creates another transaction with 2 inputs and 2 outputs. The inputs are the liquidity tokens she wants to burn, and of course the pool, again with the remove redeemer. And the outputs are the tokens from the pool that she receives in return. So in this case, she would get 1070A and 1869B. And the updated pool is the second output. So the 1070A and 1869Bs have been removed from the pool. And the datum has been updated, so the 1415 liquidity tokens that Alice burned are now subtracted from the 1982 we had before, and we see that 567 are remaining, which are exactly those that Charlie owns. And the formula for how many tokens Alice gets for burning liquidity tokens is again somewhat complicated, but it's basically just proportional. So we know how many liquidity tokens there are in total, 1982 from the datum, and she basically just gets 1415 over 1982 of the pool. And she gets the tokens in the ratio that they are in now. So the 1070 to 1869 should be the same ratio as the 1500 to 2619. So by burning, you don't change the ratio of the pool. The last operation is close, and it is for completely closing a pool and removing it. And this can only happen when the last remaining liquidity tokens are burned. So in our example, Charlie holds all the remaining 567 liquidity tokens, and therefore he can close down the pool. And in order to do that, he creates a transaction with 3 inputs. One is the factory, and note that we only involved the factory when we created the pool and now when we close it again, which also means that the contention on the factory is not very high. So the factory only gets involved when new pools are created and when pools are closed down. But once they exist, and as long as they are not closed, the operations are independent of the factory. But we just need the factory when we want to update the list of existing pools. And by the way, this list is used to ensure that there won't be duplicate pools. So the create operation that we looked at in the beginning will fail if somebody tries to create a pool that already exists for a pair of tokens that already exist. So there will always, for any given pair of tokens, be at most one pool that contains those 2 tokens. Okay, so let's go back to the close operation. So the first input is the factory with the close redeemer. Second input is the pool that we want to close. And third input are all the remaining liquidity tokens. And we get 2 outputs. One is the updated factory. So in this case, we only had 1 pool, so the list only contained this 1 pool, and this is now removed from the list. And the second output contains of all the remaining tokens, all the tokens that were still in the pool by the time it gets closed down. So the remaining liquidity tokens are burned, and Charlie gets all the remaining tokens from the pool. The code for Uniswap is actually part of the Plutus repository, and it is in the Plutus use cases library. And it's split into 4 modules that are imported by the plutus.contracts.uniswap module: on-chain, off-chain, types, and pool. So as the names suggest, on-chain contains the on-chain validation, off-chain contains the off-chain contracts, types contains common types that the other code shares, and pool contains the business logic, the calculations, how many liquidity tokens the creator of a pool gets, how many tokens you get when you add liquidity to a pool, how many tokens you get back when you burn liquidity tokens, and under which conditions a swap is valid. So I don't want to go through all of that in too much detail. It contains nothing we haven't talked about before, but let's at least have a brief look. So let's look at the types module first. U represents the Uniswap coin, the one that identifies the factory. A and B are used for pool operations, where we have these 2 sorts of tokens inside the pool. Pool state is the token that identifies a pool. Actually, in the diagram earlier, I said it's an NFT. And by definition, NFT is something that only exists once. Actually, here in the implementation, for each pool, an identical coin is created that identifies that pool. So it's not strictly speaking NFT. So all the liquidity pools have 1 coin of that sort. And liquidity is used for the liquidity tokens that the liquidity providers get. And all these types are then used in the coin A type. So A is a type parameter that's a so-called phantom type. So that means it has no representation at runtime. It's just used to not mix up the various coins to make it easier to see what goes where. So in the datum, a coin is simply an asset class that we have seen before. So asset class recall is a combination of currency symbol and token name. Then amount is just a wraparound integer that also contains such a phantom type parameter, so that we don't confuse amounts for token A and token B, for example. Then we have some helper functions constructing a value from a coin and an amount. And here, for example, we see the use of this phantom type. That's actually a common trick in Haskell. Because now if we have, for example, a pool operation that has 2 different coins and 2 different amounts for the different coins, and if the one is tagged with this type capital A and the other with capital B, then normally one could easily confuse them and somehow do operations with of the one coin with the amount for the other and then make a mistake. And here the type system enforces that we don't do that. So we can only use this value of function, for example, if we have a coin and an amount with the same tag, type tag. So as I said, that's a common trick in Haskell. That's some lightweight type level programming that doesn't need any fancy GHD extensions. Unit value creates one amount of the given coin. Isunity checks whether this coin is contained in the value exactly once. Then amount checks how often a coin is contained in the value. And finally, makeCoin turns a currency symbol and the token name into a coin. Then we have the Uniswap type, which identifies the instance of the Uniswap system we are running. So of course, nobody can stop anybody from setting up a competing Uniswap system with a competing factory. But the value of this type identifies a specific system. And all the operations that are specific to a pool will be parameterized by a value of this type. But it's just a wrapper around a coin U. And that is just the NFT that identifies the factory. Then we have a type for liquidity pools, and that is basically just two coins, the two coins in there. However, there is one slight complication. Only the two types of tokens inside the pool matter, not the order. There is no first or second token. A pool that has coin A, and coin B, B should be the same as one where A and B are swapped. And in order to achieve that, the EEC instance has a special implementation. So it's not the standard. We don't just compare, if we want to compare two liquidity pools, we don't just compare the first field with the first field of the other and the second with the second, but we also try the other way around. So a liquidity pool with tokens AB would be the same as liquidity pool with tokens BA. So that's the only slight complication here. Then we define the actions. That's basically the redeemers. So create with argument liquidity pool is for creating a new liquidity pool. Close is for closing one. Swap is for swapping. Remove is for removing liquidity. And add is for adding liquidity. Note that in the diagrams I showed earlier, for simplicity, I called the redeemer simply create. So I didn't mention this argument of type liquidity pool. The datum is a bit more complex than we have seen before, so it's not just a simple integer or similarly simple type. It's of type Uniswap datum, and there are two constructors, one for the factory and one for each pool. So the factory will use the factory constructor, and the pools will use the pool constructor. And as I explained before, the datum contains, for the factory, contains a list of all liquidity pools that currently exist, and the datum for pool contains the liquidity pool that I didn't mention in the diagram. And what I did mention in the diagram, it contains the amount of liquidity that has been minted for this pool. Remember, that gets updated when somebody adds liquidity or removes liquidity. Next, let's look at the pool module, which, as I explained before, contains the business logic, the calculations. So we have calculate initial liquidity. It gets the initial amounts of token A and B that are put into the pool and returns the liquidity tokens that are returned in exchange for those. Then calculate additional liquidity for the case that the pool already exists and somebody provides additional liquidity. So the first two arguments are the amount of token already in there. Then the third one is the liquidity that has already been minted for the pool, not the liquidity tokens that have already been minted. And the next two arguments are how many A's and B's are added to the pool. And the result is how many liquidity tokens will be minted in exchange for this additional amount, this additional liquidity. Calculate removal is for the opposite case. So given how many tokens are in the pool, how much liquidity tokens have been minted, how many liquidity tokens are to be removed, it gives how many tokens A and B remain in the pool. Check swap is arguably the central function of the whole Uniswap system. It calculates a swap. So this and this is how many A's and B's are originally in the pool, and this says how many A's and B's are after a swap in the pool, and it just returns whether that's okay or not. So in principle, it just checks that the product of the last two arguments is larger than the product of the first two. And as I explained before, it's a bit more complicated because the fee is taken into account. So in this case, it's 0.3%. So you can see that's as taken into account here. It also makes sure that none of the amounts ever drops to zero. So it's not allowed to remove all coins of one sort or of both from a pool. And that also makes sense because of this product. If one of the factors was zero, then of course it couldn't be larger than it was before. Finally, there is this LP ticker function. It's just a helper function that, given a liquidity pool, computes a token name for the liquidity token. And the idea here is that this token name should only depend on the liquidity pool and should be unique. So each pair of tokens should result in a unique token name. And in principle, it just takes the currency symbols and the token names of the two tokens or coins, concatenates all of them and hashes that, and then uses the hash of the concatenation just to get something unique. And the slight complication is here that you again must make sure that the order of coins in the pool doesn't matter. So this is why there's a condition here. So it's checked that they are sorted, and if they are not sorted, then you swap them around. So this function should return the same token name for liquidity pool with token A and B, and for liquidity pool with token B and A, which also corresponds to what I said earlier about equality for liquidity pools. Now let's look at the on-chain part. Only two functions are exported to make the validator for the Uniswap, both factory and pools, because they share the same script address. They are just distinguished by the datum and by the coins that identify them, and validate liquidity forging. So that's the monetary policy script for the liquidity tokens. But there is a lot of code in this module. And as I said, I don't want to go through it in detail. Let's rather look at the structure. So this is the make Uniswap validator function. And this function contains all the cases for factories and pools and the various redeemers. And we have the function validate liquidity forging, which is the monetary policy for liquidity tokens. And the idea here is that it doesn't contain any logic and simply delegates the logic to the Uniswap validator. And the way it does that is it checks the inputs of the forging transaction and checks that it's either contains a factory or contains a pool. Because if it does, then this validator will run. We know that this validator will run, and then the validator can check that the forging is okay. And the way it does check whether either the factory or pool is an input is via the coins that identify a factory or pool. So it checks whether this Uniswap factory coin is in the input or whether one of the pool coins is in the input. And then we just have helper functions for all the various cases. And they, look quite long, but it's all straightforward. And it's basically what I explained in the diagram, just spelled out in detail, that all these conditions are satisfied for all the different cases. One thing I should mention is I didn't use state machines, and I'm not sure it's possible. I was thinking about that, and it wasn't obvious to me. The problem is, one should think that both the factory and the individual pools behave like state machines. They are identified by their tokens, and there are these legal transitions and then the datum gets updated and so on. But the problem somehow is that sometimes we have both of them involved, the factory and one of the pools. And it's not obvious to me whether that's possible with the current state machinery. So I basically did it by hand when I wrote this. Finally, let's look at the off-chain code. Also, no surprises here. It's the usual boilerplate. We define two different schemas. The idea is that one is for the entity that creates the Uniswap factory, that only has one endpoint start and no parameters. And then once that is created, a second schema for people that make use of this Uniswap system. And all the contracts in here will be parameterized by the Uniswap instance that this first action creates. We make use of the state mechanism, so of this monad writer mechanism that is accessible via tell. And basically for all the user operations, we have our own state. We call it user contract state. So there will be a helper contract that queries for all existing pools. So then the state will be using this pools constructor and return a list of pools. In a simplified form, it's just a nested pair of pairs of coin and amount in each pool. Another helper function to query the existing funds of a wallet that will just return a value. And then constructors for all the other operations. So if they have happened, then one of those will be the state. So for example, if we did a swap, then afterwards the status will be updated to swapped. If we removed liquidity, it will be updated to removed, and so on. Then some names for the various tokens. So Uniswap will be the token name of the NFT in the Uniswap factory. Pool state will be the token name for the coins that identify the liquidity pools. Then our usual boilerplate to actually get a script instance. And the policy for the liquidity tokens, some various helper functions, then all the parameters for the endpoints. So for example, if we want to create a pool, we need to know the tokens and the amounts. If we want to swap, we must know the tokens and how much to swap. And the idea is here that one of these two last fields should be 0. So if we want to put in A and get out B, we would specify the SP amount, how many A's we want to put in, but we would leave the B at 0. And the other way around if we want to swap B against A's. Close, if we want to close a pool, we just have to specify which pool. So we give the two tokens that are in there. Remove, we have to specify the pool and how much liquidity we want to burn. And add, again, identify the pool and how many A's and how many B's we want to add. Now here we have the implementation. So start, as I said, sets up the whole system. And it again makes use of this other use case we have used before, the currency forge contract, to mint this NFT, the factory NFT that's then used to identify the Uniswap factory. Create is the contract that creates a liquidity pool. And we see all of these will be, as I mentioned before, identified by the Uniswap value, which is the result of this start contract here. So we have create, we have close, again parameterized by Uniswap, remove, add, and swap. And all these functions also make use of the functions from the pools module, these that contain the business logic. So that will be used both in the validator on the on-chain side as well as on the off-chain side in these contracts here. Swap. Pools, as I said, just queries the existing pools. So it looks for the factory UTXO and checks the datum of that. And as we know, the datum of the factory contains the list of all pools. And finally, funds just checks our own funds, the funds in the wallet, and returns them. So these all return values, or I mean, funds, for example, returns value, pools returns a list of this. But I mentioned earlier we want to write that in the state, and this is now done in these endpoint definitions. So first we have the owner endpoint for setting up the whole system, which just uses the start contract. And then we have the user endpoints, which combine all these operations that a user can do. And now there is no return value anymore, and instead we make use of this state. So we use the last monoid again, so only the last told state will be kept. And we also allow for error. So if there's an error in one of these contracts, then we will catch that error, but use a left to write it in the state. And if there was no error, we write the appropriate user contract state value in the state with the right constructor for either. So this is done here. Finally, we also have a stop endpoint that simply stops. It doesn't do anything. Just if we look at the definition here, at any time you can invoke stop or one of the others. And if it was one of the others, then recursively user endpoints is called again, but in the case of stop, not. So if stop endpoint is ever called, then the contract stops. There are also tests for Uniswap contained in this Plutus use cases library, but I don't want to look at them now. Let's rather look at the Plutus PAB part and how you can write a front end for Uniswap. There is actually one also contained in the Plutus repo. It's in the Plutus PAB library, and there in the examples folder. So there's a Uniswap folder that contains the simulation monad part of an example how to do that. And I took this and copied it into our Plutus Pioneer program repo and slightly modified it to make it more suitable for what I wanted to show you. When we look at the Cabal file for this week's code, there are two executables. One Uniswap-PAB, which will run the PAB and the server, and then one Uniswap-client, which is a simple console-based front end for the Uniswap application. And you see here in the other modules field, there's a module Uniswap, and that's listed in both. So that will contain some common definitions that are used by both parts. So let's first look at that. First of all, as I explained when I presented the Oracle demo, we need some data type that captures the various instances we can run for the wallets. And in this case, I have three. Init hasn't been mentioned before. That has nothing specifically to do with Uniswap. This is just used to create some example tokens and distribute them in the beginning. Then Uniswap start corresponds to the Uniswap start or Uniswap owner schema that I showed you just now for setting up the whole system, and Uniswap user corresponds to the other part, to the various endpoints to interact with the system. And this last constructor is parameterized by a value of type Uniswap, which is the result of starting. So after having started the system, the result will be of type Uniswap, and this is then needed to parameterize the client. This is just boilerplate. This is this init contract that distributes the initial funds. So it again makes use of the forge contract that we have seen before. And it now produces tokens with token names A, B, C, D, and 1 million of each. And actually, it also multiplies that by the number of wallets. So in this case, I want to use 4 wallets, wallets 1 to 4. So actually 4 million of each of the tokens will be forged. And once they have been forged, I send from the forging wallet to all the other wallets 1 million of the tokens. So one wallet forges 4 million of each and then loops over the other wallets and sends them 1 million each. So this is just needed to set up example tokens and distribute them amongst the wallets. This is just a helper function because in order to communicate the various contract instance IDs and other things I need, I just use helper files, and this is the file name for a given wallet. So now let's look at the PAB part. So we will look at the main program in a second. Just this here is the boilerplate I showed you earlier to actually hook up the PAB mechanism with actual contracts. So this is all boilerplate, and it uses this Uniswap contracts that I just defined with the three constructors in it: Uniswap start and Uniswap user. And in this part, this is linked with the schema. So Uniswap user will use the Uniswap user schema that we defined before. Uniswap start will use the Uniswap owner schema that we defined before. And init will use a schema without endpoints. And this part here connects these constructors with the actual contracts. So Uniswap user with argument US will use the user endpoints that we looked at earlier. Uniswap start will use the owner endpoint that we looked at earlier. And init will use the init contract that we just defined in the Uniswap module. That's just for demonstration to create these initial coins. This here is again boilerplate. So now we can look at the main program. So in the simulator monad, we execute certain things. So first we set up the whole system. We start the server and get a handle to shut it down again. And then in the end, we just wait until the user types a key and then we shut it down again. Okay, so first thing we do is wallet 1 activates this init contract. So we know from looking at the code what that will do. It will mint all these example tokens, A, B, C, D, 4 million of each, and then distribute them so that wallets 1 to 4 end up with 1 million of each of the 4 different tokens. And we wait. So, I mean, this will concurrently start this contract, but then immediately continue. It won't block. So we use this wait for state that I explained when we talked about oracles to wait until init returns. And what init will do is it will write the currency symbol of the forged example tokens into the state. So we wait until we see that, and then we remember it. And we wait until this init contract has finished. And then we write the currency symbol into a file that I called symbol.json. And we just use encode that comes from data.ason, the JSON, standard JSON library for Haskell. So we take this currency symbol and encode it to JSON and write it in this file. And we write a log message. Then again for wallet 1, we start the Uniswap system. So we use the Uniswap start constructor. And we again use wait for state to wait until we get the result. And the result of the Uniswap start, I explained that earlier, will be a value of type Uniswap. And we need that value in order to parameterize the user contracts. So we wait until we get this. I call it US. And we log. And now Uniswap, the system is running, and now we can start the user instances for all the wallets. So I loop over all wallets and activate the Uniswap user contract, which is now parameterized by the US value I got in the previous step. Here. Okay, now I have these handles, and in order to interact, to communicate from the front end with the server, I need these handles. So I write them into a file, and this is where I use this helper function CID file that I showed you earlier. So I will end up with 4 files, w1.cid until w4.cid, which contains these contract instance IDs for the 4 contracts. Log a log message, and then I just wait until the user types a key and I can shut down the server. Let's try this out with cabal run uniswap -pab. And now a lot of stuff is happening. Remember, first we forge these example tokens ABCD, and then we need to distribute them to the other wallets. Then we have to start the Uniswap system, and for that we again have to first forge the Uniswap NFT that identifies the factory, and then create the initial UTXO for the factory that contains an empty list of pools. And now we see that all the Uniswap user contracts have started for wallets 1, 2, 3, 4. If we look, we see the various files that I wrote, so we can look at those. So symbol.json is the currency symbol of the example tokens I created. So I need that to refer to them. And then we have these W1 to W4. So if we look at one of those, that's the contract instance IDs for the contract instances for the 4 wallets. And in order to find the correct HTTP endpoints to communicate with them, I need these. Let's look at the client next. So as for the Oracle, I also wrote that in Haskell using the same library for doing HTTP requests. And in the main program, first of all, I expect one command line parameter, just a number from 1 to 4, so that the main program knows for which wallet it's running. Then I read the corresponding CID file to get the contract instance ID for that wallet. And I read this symbol.json file to get the currency symbol of the example tokens. I read that with something read file coming from the byte string library, and decode comes from the ASON library to decode the JSON back to a Haskell data type. I just check whether there was an error, and if not, I invoke this go function where I give as parameters the CID, the construct instance ID, and the currency symbol. And here it's just a loop. I read a command from the console. We get to the commands in a second. And then depending on the command, I invoke various helper functions. And the commands exactly correspond to the endpoints we have, except for stop. I didn't implement stop. So we can query our funds, we can look for existing pools, we can create a pool, we can add liquidity to a pool, we can remove liquidity from a pool, we can close a pool, and we can swap, which is the whole point. And the commands is just this. So for each of those, we have a command. And in order to enter amounts and currency tokens, currency symbols and token names, because the currency symbol will always be the CS. We are only using our example tokens. I don't need that. And for the token name, because the token names were ABCD, I just use a character for that. Then it's easier to type. So for example, create integer character. So that means create a liquidity pool with that amount of the token with that token name and that amount of the token with this token name, and so on. This read command is just straightforward. It reads from the keyboard and then tries to pass that as a command, and if it fails, it will just recursively read command again, and if it succeeds, it returns this command. Then there are just various helper functions to convert something of type command into the corresponding parameter types, like create params or add params from the Uniswap module that I showed you earlier. This here, show coin header and show coins, just to make it look a bit prettier when we query the funds or the pools. And then we have the various endpoints. And that all makes use of a helper function. Last time, I think for the Oracle, I spelled that out. Now I extracted it. So I have these helper functions, get status, which we need in order to get something back from the contracts, and call endpoint. So I'm just using this library, this REQ library as last time. And here, this is the interesting part. This is the request. So it will be a post request. This is the URL, and I must give the instance ID. This is here. So this is of type UUID. So I just convert it into a string and then pack it to a text because this HTTP library expects text here. And the name of the endpoint. And the request body, that depends, of course, what parameters. So this is just a parameter here. That's the third argument in the function. The response will always be unit. And I just check whether I get a 200 status code or not. And the get status is a get request that invokes this HTTP endpoint called status, again with the CID. And it doesn't take a request body. And I have to tell it what I'm dealing with, so that's why I need this Uniswap contracts type here, and that's also why this Uniswap client executable also needs access to this Uniswap module. And then I just check if the state is empty, which happens right in the beginning because before anything has told anything to the state. Then I wait a second and recurse. And if there's a state, so it's just E, then I know that this is of type either text user contract state. Recall this user contract state, there was one constructor for each of the endpoints, but if there's an error during contract execution, I get the error message as a text. And if something went wrong, then I end in this third case. And with these two, it's easy to write all the cases for the endpoints. So let's maybe look at one at get funds. So I use this call endpoint helper function that I just showed. So for the endpoint name funds, and in this case, the argument, the request body, the argument, the request body is just unit. And I wait for 2 seconds, and then I use this get status helper function. And if I get a write, then I show the funds that I got, and otherwise I recurse. So I wait until I get a write, because in this case, this funds should never fail. There's no way that can fail. Therefore, I can safely wait forever. Get pools is similar. So it's more or less the same, except that instead of funds, I have pools now. And let's look at one more example, for example, for creating a pool. So again, I call the endpoint, I wait for 2 seconds. Now there could actually go something wrong. For example, if I try to create a pool where both coins are the same, or if I specify a larger liquidity than I have in my wallet, then I would get an error. So in this case, if I get an error, I just log it to the console. And the others are very similar. Now let's try it out. Let's start 3 instances for wallets 1, 2, 3 and try to recreate this scenario from the diagrams in the beginning. So I can start it simply by cabal run uniswap minus client, and then as command line parameter I give 1 for wallet 1, and I do the same for wallet 2 and for wallet 3. And I see here that these log messages, that the contract instance ID and the symbol for the token that I can use, the ABCD, are read correctly. So now what can I do? I can, for example, query my funds. And I see I have ABCD, 1 million each, and a lot of Loveless. Let's see, 3, 6, 9, 100,000 ADA. And I can also look for pools, but right now there shouldn't be any. And indeed, none are listed. So let's switch to wallet 1. Let's say this is Alice, Bob is 2, and Charlie is 3. And in the diagrams we started with Alice setting up a liquidity pool for tokens A and B, 1,000 and 2,000. So to do this here, you can type create 1,000 A. Remember that was of type character, so I have to use single quotes, and 2,000 B. And I get the created status back. So it seems to have worked. I can query for pools again. And indeed there is one now. So I see it has A and B, and with the correct amounts, 1,000 and 2,000. The next step was that Bob swaps 100A for B's. So let's do swap 100A for B's. Okay, let's check how many funds Bob now has. And indeed he has 100 less A's and 181 more B's. Next, Charlie added liquidity. I think it was 400 and 800. So we can use add 400A, 800B. We now check the pools. We see it's 1,500 and 2,619. Is that correct? So we had 1,000 in the beginning, then 100 were added by Bob, and now 400 by Charlie. So I think that's correct. Now if we go back to Alice, she wants to remove her liquidity. So let's first query her funds. So she has less A and B's now because she provided them as liquidity for the pool, but she has this liquidity token, 1,415. So for example, she can burn them and get tokens in exchange. She doesn't have to burn all, but in the diagram she did. So let's do this. So remove 1,415 A, B. And let's query her funds again. So now she doesn't have liquidity token anymore, but she got A's and B's back. So if we compare, so it was 8,000 here, so now it's 9,869. So she got 1,869 B's and 1,070 A's. And I think the last step was that Charlie closes the pool. So let's switch to Charlie and let's say close A, B. And if now we look for pools, then again we don't get any. So it all seems to work. Finally, I want to show how to do this without Haskell, the front end, and just use something like curl, because somebody in the Q&A asked for that. So let's see. I have, for example, status.sh. You will also find that in the code folder. And I expect one argument, that's the wallet, and then I just curl to this URL and I interpolate the content of that file, the correct wallet file given by the first parameter here and status. And because that's very unwieldy, I pass it on, I pipe it through to JQ, and then I'm only interested in the current state and dot observable state of the corresponding JSON, of the resulting JSON. So if I try this right now for wallet 1, for example, and see that wallet 1 at the moment has these amounts of the tokens ABCD. Okay, and at least that was the last status. Maybe it's not up to date. So, for example, I can do funds. Let's first look at the funds script. So that again only takes one parameter, one argument, the wallet, and that does occur to this. So same here to put the correct contract instance ID there, and then endpoint funds. And this is a post request, so I need request body. So this is unit because the funds endpoint doesn't require any arguments except the unit argument. So now that I've invoked that, if I query status again, it should have been updated. Probably it hasn't changed yet. A bit more interesting is what to do with the post requests that do have interesting arguments. For example, if now wallet1 wants to create a pool again with 1000A and 2000B. So we need a request body for the correct parameters, for the create params. So let's look at this. So I also have a shell script for that. So in principle, the curl is simple. So now again, contract instance ID, and now it's endpoint create. But the question is what to write in this body. So I have it here. So I use similar arguments to in the Haskell implementation. So first the wallet, and then the A amount, A token, B amount, B token. So maybe we should first check whether it works. So I can do create wallet, what was it, one? Doesn't matter. Let's say wallet 1, 1000A, 2000B. Okay, and now if I query the status, now it hasn't updated yet, so it's still the fund status. So let's try again. Now I get the created. So I also have a pools. Pools wallet 1. Okay, and now the status. Okay, now I see I have this new liquidity pool with A and B. So remains the question how I got this this body, because that's complicated. It's hard to do this by hand. But if we look back at the Haskell output, what I did was here, for example, for create, I always write the URL where I do the request to and also the request body. And we can actually check the code for this. So if we look at Uniswap client, this is in this helper function called endpoint. I brushed over that earlier when I showed you the code. So this is this line here where I write the request body. So I get the A, that's just a Haskell value that can be encoded to JSON. And I here in this line where I log, I just use encode from the JSON from the ASON library. So this is now a byte string, and in order to write that to the console, I need a string. So I use something from the byte string library. It's called bytestring.lazy.character8 for character 8 encoding. And so I unpack this byte string to a string and then I log it. And that's the way I would recommend in order to figure out what request bodies to use. I mean, you don't, of course, have to write a whole program. You can also do that in the REPL. So you just need a value of the correct type and then use ASON to encode it and look at the result, and then you see the shape of the JSON that is expected. And then you can use that. And then it's straightforward to do the curl request. So you don't need a Haskell backend. Once you have curl, you can use anything like JavaScript, for example, to write a front end. Okay, that concludes the lecture, and I think because it's the last lecture, I also don't want to give you homework. Of course, you can, if you like, play around with this demo and set up your own liquidity pools and do some swaps. And of course, whatever you want. I mean, you, for example, can try to write a JavaScript front end, a nice graphical UI. Or you could also as a challenge, think about whether it is possible to use the state machine mechanism instead of doing it by hand as I did. So this, as I said, was the last regular lecture of this course. I thank you very much again for all your hard work and your attention and your enthusiasm. and I hope you learned a lot and are eager to try it out once Plutus is available on the testnet and then later on the mainnet. And I hope to see you again soon in a future course about some other technologies like Atala Prism or Marlow. Thank you very much again. It was a great pleasure teaching this course.